Identifying mosquito breeding grounds. Deep learning for arbitrary-shaped water pooling region detection on aerial images. By Mpravina and Maheshi Dasanaike. This research is already published at IEEE Explorer. Click the link for further information. Epidemics of dengue fever have been recognized for more than 200 years. One modeling estimate indicates 390 million dengue virus infections per year, of which 96,067 to 136 million manifest clinically. Another study on the prevalence of dengue discloses that 3.9 billion people are at risk of infection with dengue viruses. Despite a risk of infection in 129 countries, 70% of the burden is in Asia. Keeping neighborhoods clean and free of receptacles that attract dengue-carrying mosquitoes is vital for dengue prevention. In this study, we propose and compare two different deep learning and convolutional neural network methods to detect and extract the region of water pooling areas, such as gutters, abandoned ponds, tires, and other water-retaining areas on rooftops, using UAVs-based aerial images. At the initial stage of the research, a dataset of water-retaining sources, which have uneven boundaries of water, was created using images captured from a drone camera. The quality of the captured images depends on the sensor capacity of the drone camera and the ground sampling distance. We have considered a ground sampling distance of 7 cm or larger, which is sufficient to identify the objects clearly using the classification system. The custom-built dataset contains a total of 600 images. To compare the performance of the two categories of object detection algorithms and identify the best model for region detection on UAV-based aerial image analysis, we evaluate two state-of-the-art deep learning algorithms from each category. Specifically, we select Mask-RCNN and YOLOV4 algorithm, as these two approaches have shown significant performance in their respective categories. In this analysis, we specifically focus on detecting water pooling areas using the aerial image. The custom-built dataset contains a total of 600 images belonging to two classes, objects with water and objects without water. First, all images in the dataset were divided into training and validation sets with an 80-20 ratio, respectively. Then they were annotated. VGG Image Annotator, VIA, tool is used to generate annotations for the Mask-RCNN model, while BBox tool is used for YOLOV4 transfer learning is used to address the shortcomings due to the small dataset. After initializing hyperparameters, learning rate, regularization, dropout is 0.0026, 0.001, 0.5 respectively, we trained the model on the locally collected image dataset using GPU. The two hyperparameters, batch normalization, and anchor model are used to predict the bounding box and the location of the object region in the given dataset. Finally, the test images and video clips captured using a drone camera were tested using the trained model to evaluate the model performance. In this research, we have adopted the pre-trained improved Mask-RCNN model, trained initially on large COCO datasets. The model with pre-trained weights is further trained and fine-tuned using the locally collected dataset. Also, we have fine-tuned hyperparameters of the pre-trained CNN model by manual search to achieve better results, and the optimized hyperparameters are shown in the table. Figure shows the complete system with the Mask-RCNN model proposed in this study. The model was trained and fine-tuned over 20 epochs with the softmax classifier to perform binary classification, using frame regression to get more precise information on the candidate frame position, and eliminating the part of the region of interest, ROI, by non-maximum suppression. Once the model is trained, it is tested against new generalized as well as unseen data to check the accuracy of the proposed. According to the table, the test results show that the map of Mask-RCNN is much higher than that of YOLOV4. This high map performance is the major advantage of using Mask-RCNN for this application. Moreover, the boundary outline of the detected area drawn by the Mask-RCNN has high precision compared to the bounding box drawn by YOLO. The flexibility within Mask-RCNN to draw an arbitrary-shaped contour is an added advantage for the given task. This figure shows samples of RGB test images and detected outputs of the YOLOV4 and Mask-RCNN models respectively. Side-by-side comparison of the model performance of YOLOV4 and Mask-RCNN for detecting water regions in aerial videos is presented here. The main task of the study is the detection of water pooling areas in inaccessible places using aerial images. We evaluate the performance of two deep learning algorithms for automatically detecting the water retaining areas with arbitrary shapes in aerial images. We built two complete detection systems using Mask-RCNN and YOLOV4 architecture. Superior performance in Mask-RCNN was observed in accuracy, precision and recall. By contrast, the YOLOV4 prediction is faster than Mask-RCNN. The future goal of this study is to propose an algorithm that produces output faster while preserving similar precision as in Mask-RCNN site, P-Multiganam and MB-Disanaike, Deep Learning for Arbitrary-Shaped Water Pooling Region Detection on Aerial Images, 2022 Moratuwa Engineering Research Conference, Murcon, Moratuwa, Sri Lanka, 2022, pages 1-5. Thank you. Authors wish to acknowledge the University Research Grant, URG/2021/14/E, of University of Peradeniya for providing the support to purchase the camera drone.